Imagine a world where the very fabric of reality is woven from the tiniest particles, each with its own unique properties and behaviors. This is the world of subatomic particles, a realm that exists beyond the atoms we know and interact with daily. Beyond the familiar protons, neutrons, and electrons, there lies a hidden universe teeming with particles that hold the secrets to the universe's fundamental building blocks. This subatomic realm is a place of wonder and mystery, where particles behave in ways that challenge our understanding of physics. One of the most intriguing mysteries in this realm is the strange behavior of a particle called the muon. Muons are fascinating particles, often described as heavier cousins of electrons. They share many properties with electrons but are over 200 times more massive. One of the most intriguing properties of muons is their spin, which makes them act like tiny magnets. This magnetic property is described by a number known as the G-factor. The G-factor is a crucial parameter in the world of particle physics. The Standard Model, our best theory for describing the behavior of subatomic particles, predicts the value of the G-factor for muons with incredible precision. According to the Standard Model, the G-factor for muons should be slightly more than 2. This prediction has been confirmed by numerous experiments over the years. However, recent experiments have revealed something astonishing. The measured value of the muon's G-factor is not exactly what the Standard Model predicts. It's a bit off, a tiny discrepancy that has captured the attention of physicists around the world. This discrepancy, known as the Muon G2 anomaly, is small but significant. It suggests that there may be new physics beyond the Standard Model, new particles or forces that we have yet to discover. The Muon G2 anomaly has become a tantalizing puzzle for scientists. It challenges our current understanding of the universe and opens up the possibility of new discoveries that could revolutionize the field of particle physics. Researchers are now conducting more precise experiments to measure the muon's G-factor with even greater accuracy. They hope to either confirm the anomaly or find an explanation that fits within the framework of the Standard Model. If the anomaly is confirmed, it could point to the existence of new particles or forces that we have never seen before. This would be a groundbreaking discovery, opening up a new frontier in our understanding of the universe. The Muon G2 anomaly is more than just a scientific curiosity. It represents a potential shift in our understanding of the fundamental forces that govern the universe. As scientists continue to investigate this anomaly, they are driven by the possibility of uncovering new physics that could change the way we see the world. The quest to understand the Muon G2 anomaly is a journey into the unknown, a journey that could lead to discoveries that reshape our understanding of the universe. Could it be a glimpse into a realm beyond our current knowledge? Could it point to new particles or forces yet to be discovered? The Muon G2 anomaly has become a tantalizing puzzle, urging us to delve deeper into the heart of matter. As we continue to explore this mystery, we may find answers that not only solve the puzzle of the muon, but also unlock new secrets of the universe. Why is this tiny difference in the muon's G-factor such a big deal? It's because the Standard Model, our best theory of particle physics, is incredibly precise. It has successfully explained countless experiments and predicted the existence of particles like the Higgs boson. Any deviation from the Standard Model's predictions, no matter how small, is a big red flag. It suggests that something is missing from our picture, something fundamental that we haven't accounted for. The Muon G2 anomaly could be a crack in the foundation of our understanding. It might indicate the existence of new particles or forces interacting with the muon, particles and forces unknown to the Standard Model. If true, it would revolutionize our understanding of the universe. It would mean there's a whole new realm of physics out there waiting to be explored. The Muon G2 anomaly has the potential to rewrite the textbooks. At Fermilab, a particle physics laboratory near Chicago, scientists are on a mission to unravel the Muon G2 anomaly. They are conducting experiments of unprecedented precision to measure the muon's G-factor with incredible accuracy. In April 2021, Fermilab announced the first results from their Muon G2 experiment. The findings sent ripples through the physics community. The measured value of G was even more deviant from the Standard Model prediction than before. The excitement continued in August 2023 with even more precise measurements. These results solidified the anomaly and increased the tension between theory and experiment. The world watched as Fermilab pushed the boundaries of particle physics. The Fermilab experiments have provided the most precise measurements of the muon's G-factor to date. Their findings have fueled intense research and debate, propelling the Muon G2 anomaly to the forefront of scientific inquiry. Section 4. The struggle to predict the anomaly. While experimentalists were busy measuring the Muon's G factor, theorists were grappling with the challenge of predicting it accurately. The muon, a heavier cousin of the electron, has a magnetic moment that is influenced by the interactions of virtual particles popping in and out of existence. This makes the task of predicting its G factor a complex endeavor, requiring both precision and innovation. Two main approaches emerged: the traditional ER ratio method and the more recent lattice QCD. The R ratio method has been a cornerstone in particle physics for decades, relying on experimental data from other particle interactions to infer the muon's G factor. This method, while robust, is not without its challenges. The R ratio method relies on experimental data from other particle interactions to infer the muon's G factor. This involves a detailed analysis of electron-positron annihilation data, which provides insights into the behavior of virtual particles. However, the accuracy of this method is contingent on the quality and precision of the experimental data available. While this approach has been successful in the past, it can be susceptible to systematic errors, making it difficult to pinpoint the source of any discrepancies. These errors can arise from various factors, including experimental uncertainties and theoretical assumptions, which can skew the results and lead to conflicting interpretations. Lattice QCD, on the other hand, is a first principles calculation that doesn't rely on experimental input. This method uses the fundamental theory of quantum chromodynamics to simulate the interactions of quarks and gluons, the building blocks of protons, neutrons, and muons. By solving the equations of QCD on a discrete spacetime lattice, researchers can make predictions from the ground up. It uses powerful computers to simulate the interactions of quarks and gluons, the fundamental particles that make up muons and other particles. These simulations require immense computational resources, often running on some of the world's most advanced supercomputers. The precision of lattice QCD calculations depends on the size of the lattice and the computational power available. However, lattice QCD calculations are incredibly complex and computationally demanding. The sheer volume of data and the intricacies of the calculations mean that even with powerful computers, these simulations can take months or even years to complete. This makes it a challenging but potentially rewarding approach to understanding the muon's G factor. Early lattice QCD calculations yielded results that differed from both the experimental measurements and the R ratio predictions, adding another layer of complexity to the Muon G2 puzzle. These discrepancies have sparked intense debate and further research as scientists strive to reconcile the differences and achieve a unified understanding of the muon's magnetic moment. The journey to predict the anomaly continues, with each step bringing new insights and challenges. Section 5. Lattice QCD, a new hope emerges. As lattice QCD techniques advanced, a breakthrough came in 2024. This breakthrough was not just a minor step forward, but a significant leap that had the potential to change the landscape of particle physics. Researchers had been working tirelessly day and night to refine their calculations and improve the accuracy of their models. The anticipation in the scientific community was palpable as everyone awaited the results that could either confirm or challenge existing theories. The BMW collaboration, a group of physicists specializing in lattice QCD calculations, announced their updated results. This group had been at the forefront of lattice QCD research for years, and their findings were highly anticipated. Their announcement was met with a mix of excitement and skepticism as the scientific community prepared to scrutinize their data. To everyone's surprise, their calculations showed remarkable agreement with the experimental measurements from Fermilab. This was a moment of triumph for the BMW collaboration, as their hard work had paid off in a big way. The agreement between their theoretical predictions and the experimental data was a strong indication that they were on the right track. This was a major turning point in the Muon G2 saga. For years, the Muon G2 anomaly had puzzled physicists, presenting a discrepancy between theoretical predictions and experimental results. The new findings suggested that the anomaly might not be as mysterious as previously thought. It suggested that the R ratio method might be flawed and that lattice QCD could be the key to unlocking the anomaly's secrets. The R-ratio method had been a cornerstone of previous calculations, but its potential flaws had cast doubt on its reliability. Lattice QCD, on the other hand, offered a more robust and accurate approach. Another group, the Mines group, further solidified the role of lattice QCD. Their independent calculations, conducted with the same rigor and precision, provided additional support for the new approach. The Mines group's findings were consistent with those of the BMW collaboration, adding weight to the argument that lattice QCD was the way forward. Their independent calculations, also using lattice QCD, aligned with the experimental measurements and supported the standard model prediction. This alignment was crucial, as it suggested that the standard model, the theoretical framework that describes the fundamental forces and particles in the universe, might still hold true. The success of these lattice QCD calculations breathed new life into the field. Physicists around the world were invigorated by the prospect of resolving the Muon G2 anomaly. The new findings opened up exciting possibilities for future research and experimentation. It gave physicists renewed hope that they could reconcile the theoretical predictions with the experimental findings, potentially resolving the Muon G2 anomaly within the framework of the standard model. This renewed hope was a powerful motivator, driving researchers to continue their work with even greater determination and enthusiasm. The journey was far from over, but the path forward was clearer than ever before.